Hello friends, welcome you all in this lecture series. This is my brief introduction. I'm Vineet Chabra, Assistant Professor, Anand International College of Engineering, Jaipur. Our topic of discussion is reciprocity theorem. This topic is relevant to the antenna and propagation subject of 6th semester EC branch. So let's start the topic. Here you can see the statement of reciprocity theorem. This theorem says that if an EMF, that is electromotive force, is applied to terminal of antenna 1 and the current measured at the terminal of antenna 2, that is terminal 2 is taken as a load, then an equal current of both in amplitude and phase will be obtained to the terminal of antenna 1 if the same is applied to the terminals of antenna 2. You can see the diagram. Actually, here we are taking a two antenna and we are naming them as antenna number 1 and antenna number 2. We are applying some EMF to antenna 1 and measuring the current at antenna 2. Here antenna 2 is a load and antenna 1 is a source. And then in the second stage, we are applying the EMF to the antenna 2 and measuring the current in the antenna 1. And we will see that the current will be same. Here you can say that it's a two-port network, quite visible in the diagram also. So before starting with the theorem, or you can say a proof of reciprocity theorem which we have discussed, there are some assumptions in the theorem. Assumptions are something you have to take some ideal condition to prove something. First is the EMF should be of same frequency and the medium of antenna, that is the medium between the antenna, should be linear, passive and isotropic. I think you are familiar with the term isotropic, that is equal in all direction, omnidirectional. Now the third assumption is that the generator that is producing the EMF in the emitter, that is measuring the current, should have zero internal impedance or equal in the both cases. The both cases are the case 1 and the case 2. The case 1 is when we applied EMF at terminal 1 and case 2 is when we applied EMF at terminal 2. Okay friends, now let's discuss the proof. You can see the block diagram in the above. Here you can see there are two antenna system, both, and it's a two-port network. E12 is the EMF applied at port 1 and I1 is the current due to this, and E21 is the current it is the EMF at terminal 2. So, and the internal impedances at port 1 and port 2 are Z11 and Z22, and Zm is actually a mutual impedance between two. You have to consider this mutual impedance also because basically they are a two-port network. Okay, so you can see the other parameters, that is voltage and the current, and here see that this is our port 1 and this is our port 2. Okay, now you can see very simply we are applying a KVL in mesh 1 and mesh 2. This equation, this is when we applied the Mesh theorem, you can see the equation comes out as I2 equals to I1, Zm is the mutual impedance, Z22 plus Zm. Okay, and the same is applied in the mesh 1 also. So this is the mathematical procedure, you can see. So finally what we got two equations, that is I1, the current at port 1, and I2, the current at port 2. This is I2 actually. Okay, read it I2. Here you can see that I1 and I2 both are depending upon the physical parameters. Physical parameters means EMF and impedances. Okay, they are constant. We have taken constant impedances and constant EMFs. Okay, now this is the second condition, means the second part of the reciprocity theorem, where we applied the EMF at the output port and we are measuring the current at the input port. This is our output port now. So the current at the output port now in this case is I1. So very simply we can conclude that this is my I1. Same can be obtained by the mesh analysis, Kirchhoff law. So I1 is, you can see that it is e to 1, and all the parameters that you have seen are same as the case of I2 in the first case. And now we know as the theorem, from the starting of the theorem, what we have said, we have taken e to 1 and E1 to as same, and by this we are getting I1 as I2. So very clearly the theorem can be easily verified. You can see the diagram below. Actually, what is the application of this theorem? What is the practical application of this theorem? Actually, the practical application of this theorem is to the matching of load. We all know what actually meaning of matching of load is: to minimize the reflections from the load. If you match the load, the reflection will be 0. Okay, so we'll get the maximum power transmitted through the I think it's from source to load. So this is my theorem and this is its proof. So now at last we have to discuss what actually, from the antenna point of view, what are the properties that are exhibit the reciprocity, that actually exhibit the reciprocity. They are directional pattern, means both the antenna having some directional patterns, so they exhibit the reciprocity. This is one thing. Second is directivity. Directivity, you all know that it is parameter of antenna. Directivity and the gain can be easily denoted with the D and G. So they are equality of directivity that actually we are getting. The effective length, the equality, the third point is equality, the equality of effective length. We know that physical length and the effective length are different in the antenna system. Okay, and the last is the antenna impedances, because every antenna has its impedance. So in the reciprocity theorem, what we are getting, we are getting the equality of impedances in both the system, in antenna 1 and antenna 2. So there are some important properties that actually exhibit the, because we all aware that reciprocity theorem we have studied in the circuit analysis, but it is also valid in the antenna system. And why it is valid in the antenna system, these are the points. Okay friends, so this is, we have done with the antenna reciprocity theorem of antenna system. I hope you have liked this and you have, so it is a very short topic in the antenna and propagation. So thank you so much. Have a nice day.